Okay, welcome back to another video on parametric functions differentiation. So answer the following questions on parametric functions and show clear and logical work. The path of a small ball traveling off of the incline in the x direction can be given by the function x of t equals e to the sine t plus 2t, and y of t equals sine squared t in the y direction. So number A says find the equation for dy over dx. So what we're going to do is we're going to do x prime t first, which is going to be cosine t e to the sine t plus 2, right? And then y prime t is going to be 2 sine t cosine t, right? And then dy over dx can be given by dy over dt over dx over dt. So dy over dt first is going to be 2 sine t cosine t all over cosine t times e to the sine t plus 2. Okay, so dy over dx is going to be this. And then it says find the speed of the ball at t equals 2. So speed of the ball can be given by the equation speed equals root dy over dt times to the power of 2 plus dx over dt to the power of 2, right? And then speed at t equals 2 is going to be y prime 2, sorry, to the power of 2 plus x prime 2 to the power of 2. Okay, alright, so I got around 1.228, and then we don't have a unit, so our speed is just going to be the same. So it says write but do not solve a function to represent the total distance traveled by the ball from 0 to 5, which is like the t measure. So to find the total distance traveled by the particle in the parametric functions, you can use the arc length formula. So the total distance can be given by integral from 0 to 5, right? This is given, and then our root, and then x prime t, and then y prime t is going to be used here. So x prime t squared plus y prime t squared, this whole thing dt. Okay, and I'm just going to try to write this out a little bit. So root of squared plus 2 sine t cosine t squared and dt. Okay, so this will be our answer. And in part D, use the findings in A to give the equation for D, the second derivative of the function. Okay, so we have dx over dt equals cosine t e sine t plus 2, and then dy over dt equals 2 sine t cosine t, and then dy over dx is going to be 2 sine t cosine t all over cosine t sine t plus 2. Okay, so we have to first take the derivative of this, right? So this is going to be pretty complex, I would say. So this is y prime, and then y double prime equals 2 times cosine squared t plus, actually negative, sine squared t, right? And then times cosine t e sine t plus 2, and then minus, right? We're using quotient rule. Okay, and then inside the bracket, we're going to first take the derivative of the denominator. So that's going to be first a product rule. Negative sine t, e sine t plus cosine squared, right? Cosine squared t, e sine t, and then we're going to get rid of the constant, right? This whole thing multiplied by 2 sine t cosine t. And then last part all over the denominator squared. Okay. Yeah, but then this isn't it, okay? So we actually have to say that d2y dx2 is equal to y prime all over dx over dt. So since this is y double prime all over dx over dt, so since this is y double prime, we have to say that our dx over dt is going to be at the denominator. So okay, and then since this is our dx over dt, we're just going to say that it's going to be cosine t e sine t plus 2. But then since we can like try to simplify this, we're actually going to say that our d2y over dx2 is going to be this whole thing, right? This whole thing, except for the denominator being cosine t e to the sine t plus 2 to the power of 3. Okay, yeah, this was pretty complex, but this is it for d2y over dx2. Okay. For part E, it says, in terms of t, write an equation for the line tangent to the curve at e to the sine 1 plus 2, and then sine squared 1. So since we have our dy over dx value as this one, we can try to figure out when, or like at what value of t the function is going to present these values, right? This coordinate value. So obviously we can kind of see that when t is equal to 1, we can have e to the sine 1 plus 2, and then y coordinate as sine squared 1, right? So t is equal to 1. So let's try to find our dy dx when t is equal to 1, right? So that means 2 sine 1 cosine 1 all over cosine 1 e to the sine 1 plus 2, right? Or if we use our calculator, we get a value of around 0.279. So this is going to be our dy over dx value. So in a point slope form, we're going to do y minus y1 equals dy over dx times x minus x2, right? Okay, so y minus our y value, which is sine squared 1, right, equals 0.279, our dy dx, and then x minus e to the sine 1 plus 2. Okay, so this is going to be the equation tangent to the line, or the curve at the given point. If you want, you can try to make this into a decimal so that it fits the dy dx form as well. Okay, moving on, we have number 2. So two parametric functions are given. Y equals t squared minus 4t and x equals 3t minus 9. Use them to fill in the following questions. Combine the parametric equations into a single equation by eliminating the parameter. Okay, so y equals t squared minus 4t, and then x is equal to 3t minus 9. So let's try to eliminate the parameter. So we have to like present a form of t equals so that we can fit the t equals into the first or whatever equation. And obviously it's a little bit more simpler for us to eliminate the parameter in the second equation, right? So x plus 9 over 3 is going to be t. So let's try to plug in t to y equals, so that we can put y equals in terms of x. So y equals x plus 9 over 3 to the power of 2 minus 4 times x plus 9 all over 3, right? So this is going to be our equation. this is basically it, unless you want to simplify further, but it's not required. And then it says draw a graph of the function with the directions labeled. So for this one, what we can do is that we can try to graph this using like the y and x form, but we can also try to draw like a little chart. So t, x, y. So when t is -2, what would be our x value? Our x value would actually be -15. Okay, so -9, 0 is going to be right here. And then -6, 3 is going to be, -6, -3 is going to be right here. And then -3, -4, right? -4, right here. And then 0, -3, here. And then 0 for, 3, 0. So here's a fuller version of the graph with most of the space given filled up. And then you can see that this is a parabola, right? And then that is expected because we have x plus 9 squared in our equation. So this is pretty expected, but then one more thing we need to do is to identify the direction. So as t is growing, right? As t is growing, it's moving from -9, -6, -3. Okay, so it's moving from here to, from the left side to the right side, right? So our directions are going to be labeled like these, okay? Okay, so for part C, we're going to first take the derivative of the function found in A. So that is, that's actually going to be x plus 9 squared all over 9, right? So we're going to say 2 over 9 times x plus 9. And then minus 4 over 3, right? So this is what we have. And then for y prime t, we're going to be having 2t minus 4. For x prime t, we're going to be having 3. Okay, and then dy over dx is going to be 2t minus 4 all over 3. And then we have a pretty similar shape, I would say. We also have a 4 over 3 in both of them. And then, but we have a 2 over 9. And then obviously we have t's in one and x plus 9's in the other. But then something that we have to notice in part A is that t equals x plus 9 over 3, right? So if you just plug in 2 times x plus 9 over 3 minus 4 over 3, we're easily going to be getting the same answer, right? If you simplify this, this is equal to this one. So yeah, so the comparison works. So y prime equals dy over dx, or dt over dt. Okay, so this is basically all we have. If you want, you can also write like a written conclusion saying that because the functions are, the function is this and the other function is this one, and then when you plug in the x plus 9 over 3, we get the same answer. So these two are equivalent to each other. So you can say something like that. And then write an equation of the line tangent to curve at the point when t equals 2. Okay, so obviously there are multiple ways to do this, but I think the easier way, since we already found the dy over dx, we can use 2t minus 4 over 3. So dy over dx when t is equal to 2 would be 4, actually 0, right? 0. So y minus -4, right? -4, yeah, -4. So y plus 4 equals 0 times x minus, or x plus 3. So the line is basically just -4, y equals -4. Let's just check this from the graph. So when t is equal to 2, we get -3, -4, right? So -3, -4. So it's right at this point. And obviously, since this is a vertex, the dy over dx is going to be 0, right? But then that's because So since this is a vertex, the tangent line is just going to be a horizontal line, which is also given by the equation y equals 4 and has no slope. Yep, that's it.